great opportunity. Speaker today is Lin Liu. He and I were graduate students. Professor John Ward, University of Colorado. I was on the early end of his students, and Lin was probably graduates. So Lin is an associate professor of Earth and Environmental Science. He's visiting the university with the generous support of the department's distinguished faculty early this summer. Lin earned his PhD in Geophysics at Colorado Boulder, Go Buffs, before joining the University of Hong Kong in 2015. He was a George Thompson postdoctoral fellow at Stanford University. Lost my place. He leverages a diverse range of geodetic, geophysical, remote sensing, learning techniques to investigate Earth's cryosphere, focusing on permafrost, glaciers. Lin's primary research goal is to quantify and understand the changes in cryospheric systems in recognition of his early pioneering work. One John Moore Early Career Award from the American Union for studying frozen ground. So today, that's what he's talking about: geodetic studies of frozen ground. Away.
Thank you very much. Thank you, Tony. And before I get started, I really want to extend my sincere gratitude to the department, the faculty, the students. Your hospitality really make me feel home. Well, when being here just for a month, I feel very much welcomed. And my family and I enjoy every bit of our visit here in Utah. So today I'm going to talk about geodetic studies of frozen grounds, or to be more precise, I would say, is focus on what happens when the foreground is not so frozen. This is what happens when frozen ground is not that intact or that frozen. This is a picture of my first field trip to Arctic coast of Alaska. See my friend Tim was holding a piece of chunk of ice just coming from this one. As frozen ground is thawing, ground ice would melt. In this case, surface collapse, and see that disturbs the ecosystem and hydrology, and expose and mobilize carbon. There's actually a lot of carbon being frozen in permafrost, now becomes mobilized. And in this case, the surface becomes rougher. That would enhance the exchange between soil and the air. In particular, CO2 and methane can come out from the thawing permafrost. Not too far away from where the strong thawing happens, you can see the background's about 20 meters away from the sides of this Trans-Alaska oil pipeline. Can you imagine if such strong thawing happens, it may disturb or even destroy infrastructure. Things like this happen over a Tibetan plateau where highways and railways are being threatened by thawing permafrost. My focus today is to tell you how we use geodetic measurements to study permafrost. Here's my two take-home message in case you fall asleep during my talk. First of all, permafrost is by definition is the underground thermal condition. That makes it very tricky to study, at least not very straightforward to study directly, unless you drill boreholes, measure temperature. Geodesy, on the other hand, would offer some unique tools. We'll talk about some of the tools for monitoring thawing permafrost through accurate measuring the surface movements. Could be vertical movement, could be lateral movements. Those movements associated with the ground ice changes. This is just to make sure we're on the same page. Some colleagues may not know or heard what is geodesy. It's one of the oldest branch of earth sciences, particularly concerning accurate measurements of three things: versus size, versus shape, and gravity. So here's a summary borrowed from EarthScope infographics, just showing you kind of our geodetic toolboxes. I add a few more over there. To me, it's my candy store, because really it's like a kid in the candy store. There's so many amazing things you can make use of it. But in a short talk, I'm not able to cover everything. From this fantastic toolboxes we are very happy with. I'm going to focus on two things. One is interfield magazine tech aperture radar, or INSAR. The other is global navigation satellite system, GNSS. In this context, we talk about GPS. So that's what I'm going to focus on. Geodesy has been long used in study permafrost or frozen ground in general. Show you a few photos. This is legendary permafrost scientist J.R. McKay. He actually deploy sensors like this to measure the opening and close of cracks on the surface. People put GPS receivers right over the surface of frozen ground and measuring how the things change. You also conduct, for instance, terrestrial laser scanning to look at the sinkhole as a form of thawing permafrost. So early studies using leveling, particular, starting Alaska in the early 1960s, and it's been now there's conducted around 10 sites over Arctic and Tibet on an annual basis. And modern tools such as LiDAR, such as GPS, UAV are mainly used for measuring subsidence. Satellite gravity, Janwa pioneered, has been also used for study of quantified terrestrial water storage over permafrost regions. As I mentioned earlier, my talk today focuses on two things, two tools, INSAR and the GPS reflectometry. I'm focusing on flat areas, okay? The picture on the right is by definition not flat. So this is not something what I will focus on too much. I'm gonna focus on flat ones like the ones you see on the picture, two photos on the left. In those flat areas where the surface movement would be dominantly vertical and gradual and subtle, okay? By subtle, I will show you more examples. We're talking about millimeter to centimeter level, okay? Come to the geodesy. Geodesy is really want to quantify those shape, change of Earth shape in a very accurate manner. But I kept saying permafrost, right? So, but what is permafrost? Permafrost, by definition, is ground whose temperature remain below 0 degrees Celsius for at least two consecutive years. So that's the pure definition. In other words, this is what I mentioned earlier. It's purely defined by the subsurface temperature. Okay? To help us to understand here, showing you a vertical diagram of showing how temperature, horizontal, showing on horizontal axis, change with depth in the typical frozen ground setting. So vertical is 0 over here. So there's, of course, this annual oscillation of the temperature. Okay? In the summer, this is where the red line shows. Okay, the surface ground would warm and then rise above 0 degrees Celsius. So it thaws, and in the winter it freezes. So there's an annual oscillation temperature. But no matter, okay, whether it's in the middle of summer or winter, the permafrost temperature is always below 0. Okay. So give you a sense of the depth in the north of Alaska. So this permafrost can be hundreds of meters, like 200, ranging from 200 to 500 meters. The surface is where we call it active layer. It's active because it freezes and thaws every year. So soil moisture changes, vegetation can grow. Over northern Alaska, this is about half a meter. So since, according to this definition, permafrost temperature is important, many long-term monitoring efforts, in particular, mostly based on field measurements, a borehole, for instance, concerning measuring the permafrost temperature, ground temperature. Another important variable to quantify the change of frozen ground is this thickness of active layer. Because imagine if the ground temperature changes, this thickness would change over time. Another one that's recently been accepted is the rock glacier velocity. So together, these three variables are identified by the United Nations framework of climate regarding the essential climate variable for permafrost. Permafrost is the largest cryospheric components by area. This is showing you a map of the permafrost extent over northern hemisphere. We see the purplish color showing where you can find permafrost. For instance, over Alaska, about 85% of Alaska is underlain by permafrost. Half of Canada, half of Siberia is underlain by permafrost. So estimate together, including subsea permafrost, globally, permafrost extends is about 18 million square kilometers. So that's a very large area. And note a little bit Hong Kong over there. Okay, I guess you figure out we don't have permafrost in Hong Kong. Okay, but closest site, which is what I've been studying, is over Tibetan Plateau. It hosts about 1 million square meters of permafrost. Okay, so now this is my new home. Okay? my new home. I'm really happy here because we have permafrost right in our backyard. Okay, you can recognize where we are, Salt Lake City, Great Salt Lake. There are permafrost, okay? The closest one is Masachi and Unita, and of course in Rockies. I'll coming back to this and I'll tell you a bit more about our ongoing, or at least what I'm gonna try to work on this fall to look at those permafrost in our backyard. Okay, coming back to the global picture, permafrost temperature is a major critical variable that people have been monitoring. There's a global network called GTNP, Global Threshold Network for Permafrost, includes about 1,000 boreholes that people have been measuring, constantly monitoring permafrost temperature. This is showing you a couple of representative ones that have a long continuous monitoring. So the message here is that not just one site, all these dozen sites, no matter we're talking about Canadian Arctic, Alaska North Slope, or Switzerland, or Tibetan Plateau, the temperature in those boreholes has been all rising, but at different rates. So globally, take an average from 2007, which is sort of the recent IPY, International Polar Year, to for this one decade time window, global temperature in permafrost rise about 0.3 degrees. Of course, you can see here that the colder areas, actually the rising rate is faster, whereas in the warmer areas, because there's a phase change, ice melting in the water, so the melting, the thawing, the temperature rising rate is slightly slower. So that's alarming, and so that causing, for instance, the thickness of active layer being changing. This is also from a couple of in situ measurements, data site, the in situ measurement sites over Tibetan Plateau here, example, that's been the active layer being rising, the thickness being thickening. In addition to that, the ground ice melts. If you recall my photo showing the ground ice melts, rock glacier would speed up, and last but not least, surface would go down. Okay, so how the surface would move associated with the change of the frozen ground. On the annual cycle, it's happening every year. In the middle of winter, active layer is completely frozen, and the pore space within soil layer being filled with ice. Okay, and as active layer thaws out throughout the summer, the pore ice melts into water, volume decreases. There's also soil can compact and its own weight, so the ground naturally goes down throughout the summer, and the reverse things happens from summer to winter as the ground refreezes. So there's this natural subsidence and uplift cycle. The amplitude of this up and down movements is about 1 to 10 centimeters. So this the magnitude, how much going down up, is related to how much soil water content in the active layer. So we can turn around by measuring the surface subsidence, the annual cycle. We can actually infer how thick the active layer thickness is. So this is on the annual cycle. But if we talk about decadal warming, as I showed you earlier on, permafrost continues to warm, thaws out, okay, and active layer becomes thicker and thicker over time. So if near the surface of permafrost still contains a lot of ice melts, okay, the melted water drains away, then causing the natural, also a long-term subsidence on the ground. So such subsidence is subtle. It's only millimeter to centimeter level per year. So it's very small. But turns out we have a very fantastic tool called INSAR, which is very suitable to measure such a subtle movement. It's an active radar sensor that's floating around, floating above us. It depends on the sensor. Every 1 week or 1 month, it's able to measure deformation of a very large area, typically 1 degree by 1 degree or 1,000 kilometers by 1,000 kilometers, offer a very good spatial resolution on the order of meters. All right, so I'm showing you another example. That's one of my first papers on this topic. This is using historical ERS from Europe Space Agency. Look at northern Alaska, this Poudre Bay. Then what this map shows is how the ground moves down throughout the whole thaw season. That's from early June to end of August, over 3 months roughly. So color shows, okay, the blue means 0 over the dry bed area. Riverbed is not, but permafrost beneath it, so the ground remains stable. But over the rest of the areas, the ground moves down over the summer by 2 to 4 centimeters. Then picture on the right showing you the time series, because we have repeat INSAR measurements over time. So it is showing the time series. We can go back to 1992 when the first satellite was launched. All right, so the cross points are my INSAR measurements. Okay? So if we are lucky in certain years, like in 1996, where I have 3 measurements. All right, I was bold enough to fit a line, but it's not just one line. I was trying to fit all the lines because, well, I have my own model. It's not a simple linear model or no sinusoidal model. So I was really like hesitating or suspicious about results because there's a lot of due to the limitation of the data. Okay, we use because the data only 35 days repeats. The C-bands, okay, there's a lot of areas that we don't have measurements because of loss of coherence. But apparently this inspired people, or this sustained my interest for many years. So I'm going to tell you that after that, we have made many achievements and advances over decades. So the background is that both INSAR community and permafrost community have been growing over the past decades. So the bridging between these two communities becomes natural and uncommon. And people realize this INSAR can be useful for permafrost. So it's being incorporated, this particular techniques being incorporated into some of major permafrost research programs. Just name a few, for instance, European Space Agency, ESA, has its permafrost CCI, Climate Change Initiative, has used quite a lot of INSAR for this initiative. NASA has a above mission Arctic boreal vulnerability experiments run for about a decade. INSAR is important components in that. There are others that I'm not going to read through. And permafrost was not regarded as a main scientist target for, at least for INSAR, was volcanoes, earthquakes, tectonics being the main force, or glacial movements were the main interest. But now it's being featured as a scientific target, including, for instance, you may have heard of the NASA ISRO mission called NISA. There's also a planned future mission from Europe called ROSE-L. In the meantime, SAR data become accessible. When I first did my first study, you have to wait for several weeks to months waiting for my data. That's from the WinSAR consortium. Now, many data are available, in particular Sentinel-1, which is a game changer in my view. INSAR processing is being streamlined. Okay? I spent 2 years of my PhD trying to figure out how to generate interferograms. But now there's a lot of things just interferogram being generated, and you just for scientists, for non-INSAR experts, just use interferogram as your data. All right, and then it's been over the years being applied to not just Alaska, to all over the major permafrost regions, because we have 18 million square kilometers of area to look at. All right, so if you're interested, we just had a review paper came out last week. Just summarize the advances of INSAR analysis for permafrost terrain. But next few slides, I will kind of highlight a few changes we made through the community and my own group. First of all, not just one particular sensor, they are all different spacecrafts carry similar radar sensors, as I shared you earlier. So this example showing you, okay, we can use the Japanese L-band SAR sensor called pulsar, and we can, in addition to look at very large area, we can focus on very small areas. So this is still north of Alaska, showing you the pipelines, reference, that force. So this lakes, many numerous thousands, not tens of thousands of lakes formed because of melting of thawing of permafrost. Some lakes could drain. This is, you can see the drainage because the bank failed, drain over the lake and absorb this dry land, which is a good target for INSAR because INSAR cannot tell easily the lake water body, but it can sense the deformation over the land area. So it used to be a lake, now it's drained, but turns out there's still a lot of brown ice there. So over this portion of the drained lake basin, we see very large subsidence, because let's just tell us this reach of high amounts of water and ice, ground ice content. We drag a ground penetrating radar over this lake, and we did confirm there's actually a large amount of relatively large amount of ice compared to the surrounding areas. So people use it, especially by using Sentinel-1, and able to look at sort of like continental scale. This is over the north eastern Tibet. This is the scale size of this area. This you have a color scale bar. This is 100 kilometers. Now people can using INSAR to map millions of square meters of areas of subsidence, but the message is still very similar. So in terms of the seasonal subsidence showing here is on the order of this is on the order of a few centimeters. If you look at trend, it's millimeter level. Still subtle, but it seems to be very consistent no matter whether you look at Arctic or Tibet. Now we also have a frequent and continuous acquisition. This is an example using the German TerraSat X sensor. The repeat cycle is 11 days. So this is look at Svalbard, Advent Island, Longyearbyen somewhere over here. And there's a borehole over here, and they're showing you a time series of the INSAR measured subsidence followed by an uplift. So you can see we have very regular 11-day apart measurements, much better than what I had, like only 3 points a summer. We can also look at disturbance. This disturbance could be due to wildfires or human activities. Last week at Sesamo TS talked about human activities, but this one is a natural fire. This happened in the tundra area, highland tundra. This is more familiar with wildfires in forests. In tundra areas, fires are rare. This is cold and the vegetation is low. But this one, Endowed River fire, burned 2007. It was the largest tundra fire in the recent 50 years. The burn area is more than 1,000 square kilometers. Just give you a sense, local context. The Great Salt Lake in 2022 is about twice as the burn area. It's a huge burn area. So we were able to look at how the permafrost beneath the burned area change. This is what happened, the subsidence in terms of up to about 2-ish centimeters before the fire. But after fire, because the ground thaws, ground ice melts, actively become thicker, and the subsidence also increases, very obviously. And this is the third one is taking this minus that. Very nicely, you can see the fire burn area. We can even see, okay, this certain areas, the severity is more than the other. Nicely, we're picking up another one, small one, next to it. Next is, in addition to satellites, there's also airborne and ground-based platform, or you can put SAR sensor over there. It's showing example from NASA above mission. It's flying UAV SAR and carry the SAR, L-band and P-band sensors beneath it, and repeatedly flew over those strips in most of the Alaska region and the western of Canada. And this is showing you a strip over here in northern Canada. Still showing you the subsidence over a few months in the summer. The scale is still the same as I did before, okay, it's 0 to 5, but giving you a lot of fine detail. The spatial resolution of this one is about 2 meters. So you can look at a lot of fine detail deformation and associated with the subsurface processes. Oh, by the way, feel free to interrupt me if you have any questions. All right, so those are all related to subsidence, but you would maybe wonder if we measure this centimeter subsidence over a summer season or millimeter level of subsidence, what's the big deal? Okay, so we're trying to push from the subsidence to higher level products that can be really useful. For instance, I mentioned about active layer thickness. We can do that. But we can also people start to use INSAR to retrieve soil moisture and characterize timing of freeze and thaw transition. And the last one showing the example is by Zoe Beck and Mayer. they use INSAR time series to kind of infer the ground ice content beneath active layer near the surface, near the top of permafrost, where they show that this is the final products derived from INSAR. Purple showing that interface has rich ice content, and the gray area are where the ice content is poor. All right, so but I will be very committee has been very happy with INSAR, but nothing works perfectly. There's still a few standing issues that keep me awake at night. One of the issues, I just had attend a webinar this morning, is related to the change of soil moisture. In cold regions, especially in active layer, the soil moisture changes constantly, and the largest change is between freeze and thaw. Okay, freeze soil moisture is close to 0. Thaws like 20 to 50 or 90%. So there's a lot of strong change in soil moisture. It turns out it's getting into a bit radar signal processing. It turns out the soil moisture change can generate fake deformation signal. So we've been trying to be careful, but there's still not a very effective ways to remove, even though we now have a way to identify possible areas or signature affected by soil moisture. Another one, actually I had a quick discussion yesterday with Menghan. Over some areas such as dependent plateau, where we have both tectonic movements and permafrost movements. INSAR measures the deformation, which is a combination of both. So in those areas, it turns out it's not always straightforward to separate. Okay, here showing you a study done by my former student, G, who's now a postdoc at the UAF. This is showing you the INSAR line site is something about this geometry that look at trend over several years. And you can easily pick up the movement across the faults. There's a major fault, Quantum fault. This is a strike slip fault, but we can still reflect in the INSAR. In the middle, where you see the red area is where we think is related to permafrost. So it's not always easy to separate those. One of the ideas is that for tectonic, we can either model, if we're only interested in deformation due to permafrost, we can model tectonic movements and remove it. Or we can use some signal processing techniques. In this case, is ICA, independent component analysis, to separate signals due to deformation, signals due to permafrost, which tend to be local and lower short wavelengths, versus tectonics, which tend to be longer and, of course, associated with faults. Last but not least, INSAR fundamentally is a relative measurement. It's very accurate, but only accurate in terms of measuring the difference between the other side of the room to this side of the room by millimeters. But if the whole room moves by 1 meter, INSAR is where it's failed. So in order to tie relative measurements into absolutes, we usually need a reference. Okay? Reference in permafrost studies, we would either assume or find exposed bedrock, okay, or assume some places for instance, dry riverbeds, there's no deformation. But in many cases, well, if you go to north of Alaska, there's literally very few exposed bedrock. So you kind of have to make a lot of assumptions. We always worry, like, are those assumptions valid? All right, so in order to validate, you have to kind of compare with ground measurements. But ground measurements is always not easy. So I usually get this lot of questions, like, why not use GPS? Right? GPS is another way to very accurately measure the deformation. Yes, there are plenty of GPS stations or GNS stations in Arctic permafrost, showing the map. There's more than 200. Okay, none of them is this is a different network. None of them is for permafrost, though. Okay, Tony used to install one of those over Greenland. So that was 1995. Unfortunately, it's a shame that it's decommissioned. But this is, for instance, this is a GNet network. It's mainly to study the isostatic rebound. Okay, there's other studies in northern Canada for study the ionosphere, and this is the boundary observatory. I will come back to this. It's for, of course, it's for tectonic studies. None of them is really for permafrost, right? So I look at one of them. This is the station is SG27. It's right on over the north coast of Alaska. This is what it looks like. This is This is part of the Earth scope plate boundary observatory. You can tell from the name, it's mainly for study the plate movements. All right, so people have been have tried very hard to deploy or install this one, and they put this is a 3.8 meter antenna above surface sitting on a wooden monument, and they want to make sure this is stable, right? So the drill borehole, this is 5-meter borehole into the ground, and make sure the monument is frozen deeply into permafrost. Okay, so we want to use this and see, well, is this useful? Okay, now this is what typical GPS will give you. Okay, so you look at what's shown here is the position of this receiver in the how that change in the vertical direction. Of course, it can have throughout horizontal direction. I'm showing only the vertical components, and this is in range from 20 to plus minus 20 millimeters. Okay? And this is, by the way, this is produced by Nevada Geodetic Laboratory. This site started operating in 2002. It's showing this continuous measurements over time. And the blue is the noisy vertical components, but you can fit this line doing very nicely this annual signature. And that's due to the loading, surface loading associated with the surface water mass, and this secular trend associated with the plate movements. Okay, so then what our message here is, in this particular case, is this useful? Because it tells us the whole thing is frozen deeply in the frozen ground. Okay, it's moving with the solid earth. The times it's showing here has nothing to do with the permafrost, because it's related to the solid earth, okay, plate movement. Okay, so in this case, I would say it's not useful for permafrost studies. Well, compared to INSAR measures the surface, measure how the surface goes up and down. But there's a mismatch between what GPS and INSAR would do. Okay? So I wasn't too happy until I talked to Christine Larson. Christine came up with this very innovative way to look at to use GPS signal. Well, mostly maybe 99% people using GPS is using the direct signal sending from the GPS satellite to the receiver. That should give us very accurate measurements of the position. Well, there are also signals that indirectly come into the receiver. Okay, some signals will be reflected from the surface and now back to the receiver. This is bad because this is what we call multipath, because that would interfere with the direct signal and make your positioning accuracy to be worsened. Okay, so this is something that you normally would compress. You only would want to throw away this kind of reflected signal. But Christine want to make sure, made it the noise to be very useful. In this case, the idea I'm trying to explain in 2 minutes, the idea is, as the satellite is flying in different elevation angles, there's one elevation angle, there's another elevation angle. For these two different reflected signals, the interferometric pattern with the direct signal will be changed because that depends on the elevation. Okay, so by tracking how the interferometric pattern change with elevation, it turns out we can know something about the surface. In this case, this one thing we can tell is this geometry. We can use how the multipath interfere with direct signal to tell what we call, what she coined as reflector height, which is the phase center of the receiver to the surface of the reflector. Okay, so in this case, we have this a very nice setup now, okay, because this whole thing is deeply frozen, and this is wooden monument supposed to be rigid. So we're basically using that as a reference, because if the ground goes up, okay, in this case, then the reflector height would be smaller, okay? And of course, if the ground goes down, the reflector height gets larger, right? So it becomes very simple retrieval because GPS interferometric reflectometry give us H, and we just take minus of delta H that tell us how the surface move up and down, okay? So that's exactly what we want. And one more note is that if the surface is covered by snow, okay, then the GPS, the reflected height changes actually reflect the change of snow depth. I'm going to show you our results. This is that side. Each dot is showing you the reflected height, how it changed up and down. Okay, over from January 1st to December 31st in one particular year. So you have this measurements every year, sorry, every day actually. So when you see a lot of large oscillations, that's related to the change of snow depth. Okay, snow comes in, accumulating, and snow melts, and so on and so forth. Okay, so that's being used in several stations across the globe to measure snow heights. I'm going to focus on this time window from June to November when there was no snow on the ground. Okay, now we can zoom in. This is what I was interested in. This is the elevation change associated with the ground, frozen ground dynamics. But I've already shown you from INSAR measurements. Okay, from June to end of August, the ground goes down and then refreezes back. But this is on the daily, at the daily intervals and from independent measurements. Okay, so we can do this every year, not just this particular year. So this is the one showing 1 year, 2013. I just want to put that into one particular plot that will have a 12-year. So that's why they all look like subvertical because they shrink them into this new plot. But we have this 12 years, so measurements only during the snow-free days. So that turns out this can give us a lot of information and can recheck what tells us. So it represents, again, the ground goes down every summer. So that's what I told you. And in this case, the magnitude ranges from about certain years is 5 centimeters, certain years is 12 centimeters in this GPS IR time series. Of course, now I want to relate that to the temperature. Okay, this is showing you the time series of what we call thaw index in the degree day. So that's accumulated degree day of thawing. Basically, just summarize a daily temperature when it's above 0 degrees Celsius. So that's the way to represent how warm a summer is. Because the higher the thaw index is, the warmer the summer is. Then highlight 3 warm summers. Okay, very happy to see that because in the warm summers, the ground went further down. Makes sense, right? Because it's warm, okay? The more ground ice melt. Of course, there's always headaches. What about this year? Okay, this summer was actually the warmest, but this was normal, okay? So there are always exceptions. All right, and also if you look at, all right, my INSAR analysis is trying to look at trend. I give you one number over trend, but look at decadal time series from GPS IR. It's not a linear subsidence. So it's for the first 8 years going down, but then it goes up and then goes down. This actually kind of subdecadal oscillations. All right, so what that tells us is that there's no simple, it's definitely not a simple linear trend. It's not always correlated with temperature. Okay? All right, so to summarize, we find out, okay, turning noise into observations, in this case GPS IR, are uniquely variable for studying permafrost in different ways. It's continuous daily measurements compared to my INSAR only a few weeks to a few months. So you can better quantify this cyclic and also non-cyclic, regular and irregular movements. Some of the GPS stations, including the one I mentioned, SG27, they're operating for this 10 years or even 20 years. When we talk about climate change, it's not something that 5 years is not appropriate. So you need long time series like what GPS can give us. And also, GPS IR turns out it's not only give us this subtle elevation change on the ground. It can give us soil moisture. Here, an example done by another student, and retrieve using GPS IR retrieve soil moisture that is shown in blue, and compare with in situ probing soil moisture sensor at 5 centimeter depth. This is actually very good agreement. Okay, GPS IR mentioned can give us snow depth. Okay, so all these variables, elevation change, soil moisture, and snow depth, they are all important for us to quantify permafrost dynamics and hydrology. Okay, and also go back to INSAR now. This definitely is a potential synergy with INSAR. Okay, So we can use results like those I showed you earlier as a calibration and validation for INSAR, because there's not much ground-based measurements of elevation changes for us to compare with spaceborne ones. And INSAR measurements has temporal gaps, could due to the loss of coherence, could due to each sensor has its lifespan, maybe 10 years, then there was a gap, and then there was another gap. For instance, there are several gaps between those L-band sensors that I think GPS can help us to tie those measurements with gaps. Of course, it can serve as reference points. All right, so if you're interested in learn more about GPS for eyes, we actually have an expert in the audience. And Tony Piba and I, we just had this chapter contribute this whole book, GNSS for monitoring for terrestrial environments. In this chapter, GNSS for the cryosphere, we summarize the use of GPS. Well, my permafrost, you already know about most of it, but you can, if you're interested in, talk to Tony or refer to this chapter to learn how we can use GNSS for ice mass balance, glacial dynamics, glacial isotopic adjustment, and snow. So I've talked to you about these subtle measurements or subtle deformation, millimeter, centimeter level. But in permafrost region, there's also a broad thawing. Okay, thaw lakes is one of them. This is another example. Okay, on this side, you don't even visually see, but INSAR or GPS can tell you. But this is another site that can always see the thaw occur very rapidly. I was standing there. This was a site we visited last summer over central Tibet. This is literally a landslide in frozen ground well that because of melting of ground ice and slope become unstable and collapse. What's also interesting, by the way, it's called retrogressive thaw slump. Retrogressive means that the head wall, in this case, is about 2 meter height, is retreating every year, okay, upslope. And that's different from a typical landslide. So this is students, another students. I do have female students, by the way. And this is a paper just came out 2 days ago on GLL. So she used applied deep learning to automatically identify those retrogressive thaw slump from satellite imageries. This is showing a time lapse from 2000, same region. 2016 is the beginning of the time series. Right here. Okay, and you can see here, it's over time. Every year is gradually expanding. There's also new thaw slump happening. So we were able to look at the whole Tibetan plateau. Again, this is more than 1 million square kilometers. All right, so look at each color boxes showing you over this grid how much the area increased over these 7 years. Okay, so we can do this over the entire Tibetan plateau. Well, the headline of this paper is really to show is within barely 7 years, the number of those actively deep thaw, retrograde thaw slump is nearly doubled from a little bit more than 1,300 to now more than 3,000. And the total area quadrupled. Okay? This is, we are seeing the climate change or the landscape change in response to the warming climates right in front of our eyes. All right, last, still about thaw slump, because I mentioned this millimeter, centimeter, right? So it's really small, but there are other geodetic measurements that can help us to quantify this large subsidence or large elevation change. This is still over the central Tibetan plateau. This is very noisy because it's still in the preliminary results. This is done by colleagues from ETH in collaboration with us. Zooming in this area, each of this is an active retrographic thaw slump. Okay, you can see there's certain areas showing red. That's showing you the elevation drop by 10 meters over barely 8 years. So we're talking about the subsidence associated with thaw slumps that on the order of meters is deep thaw. Okay, there's also very interesting in seeing that related to the active zone. All right, so where the thaw material goes, okay, a lot of it just deposit, accumulate over the slump floor area. So we do able to form this particular measurements to also quantify over the slump floor area actually is gaining, right? It's rising up on the order of a few, maybe 5 meters at the most over 10 years. All right, so save the best to last. Let's talk about our background, our backyard permafrost. Okay, this is the picture I showed you earlier. I'm still learning a lot from colleagues like Liv. And this past weekend, I took my family to over this resort. You know, this is a snowbird. It's open in the summer, and this is this aerial tram, iconic aerial tram. Right when I get off the tram, okay, I told my son, "There's a rock glacier over here." Okay, right there. Okay, and I'll just help you to outline this. It's not easy to see from this low resolution image, but you can kind of see this this up and down furrows and ridges that indicate something is moving. Okay, in this case, this particular landform called rock glacier is a mixture of ice and debris, and by definition, is permafrost because permafrost means the subsurface temperature is below zero. It's less ice in there, and under gravity, permafrost creep and forming this. And while I was enjoying my time and I take my family because I'm taking my sabbatical, right? This is my son who will have. Well, this is this rock glacier over there. Okay, he heard me talk about rock glacier all the time. Finally, I was able to point to him what is rock glacier. While I was enjoying that, my poor students, Joe, was in Hong Kong and doing all this fancy processing that should make Lev and Mike happy. Why I think they should be happy is because he was able to quickly. This is the same rock glacier. Let's just flip it. So this is the toe area. That's this. Right. This is from Joe. Okay. He was able to using INSAR to map how this landform is moving. Okay, downslope. This is showing you the downslope movement from 0 to 50 centimeters. Well, Lev, you can correct me if I'm wrong, but because you did some measurements over there. All right. Now he spends some time over there. Over the weekend, he was able to produce this kind of results over 800 rock glaciers in Utah, almost finished. Right, so this is another example, two examples, Wasatch and Timpanogos. This one may be controversial because people are still arguing whether it's rock glacier or debris covered glacier. But this is what's going to motivate me to work with Lev, Mike, Tony, and students, Yvonne and others, to try to understand where they are, how they move, and the composition and processes behind. INSAR is one of them, but of course we have in situ measurements, seismic, resistivity, and so on and so forth. We're doing the multi-geophysical investigations. We're still at the early phase, even though Joe has finished most of the INSAR work. But come back, check with us. We will tell you a lot of exciting findings about our backyard. I think that's important. All right, so here's my summary. Permafrost is fundamentally defined by surface temperature. So it's the changes are driven by thermal, a lot of driven by thermal, but also hydrological and biogeochemical processes. So geology only scratched the surface, but still useful. It measures the deformation very accurately from both in the vertical deformation associated with the freeze and thaw of ground ice, and also lateral movements due to permafrost creep. So such unique observations, hope you agree, are related to the spatial temporal change of ground ice content. But we still need to refine. And many of the algorithms traditional for defined for earthquake volcanoes would not work for permafrost. We still need to refine those. We still need to incorporate our knowledge of permafrost into those measurements. We still need to incorporate with many other observations. Mentioned near surface geophysics, but ground measurements of temperature is essential. Soil moisture and vegetation, and so on and so forth. Okay, we need to incorporate measurements into models. Working with modelers, trying to incorporate those millimeter deformation into model. It's not straightforward. We are working on that. Look at the future. Permafrost would continue and to thaw, even at accelerated rates. So it's going to happen, going to continue to happen, and it's going to happen on a global scale. That just call more monitoring efforts like geodesy, geophysics, earth sciences would be very useful. And one last thing I would highlight is rock glacier velocity. That's what I just told you. This is what we're gonna be very happy. I'm very jealous of you because I have to fly 5 hours to Tibetan Plateau, suffer from high altitude sickness. But this looks like I can bring my son to look at rock glaciers in Utah. So with that, you have my email. I'm sitting 365. Find me if you're interested, or I'm very happy. I'm available. My time is very flexible, and I have a lot of time. Thank you very much. Yes.
Sarah.
I have a bloody name question. I was wondering how the in the permafrost area in the subsurface where you have vegetation, how is it quantified and how is it mapped?
Right. So I will come back to this figure I showed you at the beginning. The short answer is not straightforward because permafrost recorded the definition is subsurface ground temperature. So traditionally there were mapped. If you talk about 1992 version, it was mapped by geologists based on surface geology, a lot of them, and with constraints of borehole measurements. But the one I show you cannot easily go back. But the one I show you on the global map, or it is for the northern hemisphere, is infer from the remote sense land surface temperature, which is from MODIS. Okay, this certain remote sensing method can tell you the surface temperature. From the surface temperature, you throw in ground thermodynamics and infer the subsurface ground temperature. And you have to worry about snow and so on and so forth. But that need to be validated because especially not just flat area with vegetation, a lot of like mountainous areas that those would not work. This is where I think permafrost, like rock glaciers, would help because rock glaciers would help to us to refine the mapping of permafrost map. And this map has been updated every year because permafrost has been degrading, the area has been shrinking. Mm-hmm.
And I noticed that there's somewhat correlation, for some region, but some other.
Yeah. Okay.
Second question is about your. And I was wondering the thickness of.
Okay. Yeah, thank you for your question, Menghan. For some reason, I cannot easily go back to the slides. Well, like first of all, I don't have to refer to the slides. Okay, so in SAR, this even for one satellite, it can fly from north to south and from south to north. So this is what Menghan mentioned, ascending and descending. So from that, you can actually constrain even to separate the vertical movement and horizontal movement. But his question is not about that. His question about, because INSAR can tell us in terms of time scales, the seasonal subsidence and the long term. And he noticed there seems to be a correlation between the seasonal and long term. So one physical explanation for that, this is not my study I mentioned. One explanation is also always related to the signature related to ground water and ground ice content. You can imagine if active layer is wetter, there's more ground ice in permafrost. So wetter area, wetter active layer would correspond to larger seasonal subsidence, and this ground ice beneath wetter active layer, and the permafrost would thaw. So that's one explanation. There's not might be a caveat though, because this is what they call idealizing problem. You have, especially you have a coarsely sample time series, and there might be a correlation between seasonal and subsidence. It's because there's an idealizing, there is a contamination among the two. But that's what I think, for instance, you have a daily measurements like what GPS IR gives you would help you to constrain that better. Oh yes, when you refer to thickness, I was thinking about is kind of the depth, right? Or the it's a land, kind of think of a landslide, right? And it's not the thickness that I think matters. It's related to kind of the volume change or the depth change of the thumb. Could you remind me what the question is? What determines depth? Yes, this is a lot of related to the thickness, the presence of ground ice. You have a ground ice, like 100% pure ice near the surface, and the melts. That would control the thickness. And the head wall I mentioned is about 2 meters. And when we visit there, we can visually see there's a thick layer of ground ice, which is exposed to air. And that's why this head wall has been retreating over years, because it's been constantly exposed to warming.
I have a more basic question
Yes.
about that same observation.
Yep.
So you're showing the seasonal up and down, but it's also the long-term items.
Yep.
And flat area,
Yep.
permafrost. So basically, if it's subsiding, then the water's got to be going away somewhere.
Yes.
Is it evaporating, or where? You know, what's happening to the water?
Yes. Yeah, we don't know where the water goes. So it's assumption, right? So, well, if you talk about the watershed, this is another scientific problem. It's like water balance issue. So we have a watershed, right? So there's a lake, there's rivers, then what's the balance of water? So given Tibetan example, there's many lakes, right? So when you talk about the lake level change, people mostly attribute it, well, depends on where the lakes are, but mostly attribute to the change of precipitation, actually. Change of precipitation to the water level change. And of course, the secondary is the glacier melting. Permafrost was the largest unknown. What's the contribution of thawing permafrost? Where water from thawing permafrost, how much that goes to go to the lake? So now we're thinking it's about 10%-ish. So it's related to, in the more general, related to your question. But we don't know. We don't know unless you do, for instance, isotope water chemistry. You can trace the melting of water from thawing permafrost. But it's very limited understanding of permafrost hydrology in general.
Less rainfall and so
Yes. 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 Yeah. Sarah?
And Atkinson. Do you have any discriminating factor? I'm thinking about something like the permafrost you are expecting mostly only the vertical signal. For example, the ratio between horizontal signal and vertical signal as a discriminating factor, saying like if I have that amount of horizontal movement, it cannot be the permafrost.
Yes and no, right? So if it's a purely flat area, then yes, the deformation due to frozen ground changes is vertical. But we also mentioned the lateral movements. Then of course, tectonic movements can be horizontal components as well. So our now way of thinking is more related to the spatial signature. Because if you have a fault, the movements is different across the fault, right? And then so that's where we're thinking, because we're thinking about in terms of the spatial signature, not necessarily in terms of the deformation direction. The constraints also, because INSAR, if we talk about one geometry, it's a one-dimensional measurement. It's line of sight in this direction. It's actually mostly similar to vertical, but also pick up some horizontal movements. And that's the issue we have to deal with. Yeah, there was one. All right.
Sometimes it's been a long time since I thought about it.
Yeah.
But between 0 and -5, water is not a binary.
Yeah.
What are the options? Liquid water.
Right, right. So the short answer is using in situ measurements or near surface geophysics. Geodesy cannot help. It's only see the surface. So last time I talked about there's one particular geophysical technique called nuclear magnetic resonance. It actually can directly tell the difference between liquid water and solid ice. But not in the active layer setting because it's too shallow. For that particular method, it's good at measuring deeper, tens of meters to up to 100 meters. There's geophysics in the room. Other methods may be able to tell, but active layer is not. It's hard in the sense that because it's relatively shallow. It's 50 centimeters, and most direct way may be in situ ground-based soil moisture sensor and the temperature sensor. or laboratory setting. Yeah. All right, thank you very much.